The next talk is called Derflow. I don't know how to pronounce it. Distributed deterministic dataflow programming in Erlang. And Manel Bravo, Songnai Lee, and Peter van Roy have been participating in this together with Christopher, who will give the talk.
Okay, cool. Hi, thanks. Okay, so this is Derflow, distributed deterministic data flow programming for Erlang. So this is kind of a joint venture between the university in Louvain-la-Neuve in Belgium and Basho Technologies, and I represent the Basho Technology effort here. Okay, so so background about the project. This is not working, which sucks. Background about the project. Basho and the industry partners Rovio and Trifork, along with a series of universities in Europe, are under a FP7 program as well called SAKE-free. This project focuses on convergent replicated data types, or conflict-free replicated data types, called CRDTs. So I don't know if people know about those, but it's very much like Erlang is the reference implementation. So we're not really focusing on Erlang at all. We're using Erlang to build the reference implementation for CRDTs. And in addition to building a database that will be the reference implementation for CRDTs, we're also building a programming language, which you'll see, this is the start of it, is a subset of Erlang that does distributed data flow programming over CRDTs. So the work is very similar to Bloom, which is UC Berkeley's language for doing distributed, like disorderly computation over lattices, bounded joint semi-lattices to be specific. And it's very similar to LVARs in that the primitives are similar. The guarantees that we make about the monotonicity guarantees are also the same. And it's not covered in this paper, but we implement some of the ideas that come out of LVARs, such as threshold reads and things like that. And the key focus is we want to write a programming language where we can guarantee, no matter how it's distributed over threads versus in a distributed environment, we want to guarantee that the results will be deterministic or correct. And we want it to be fault tolerant as well to failures. So I don't know, show of hands for CRDT, so I can. No? Okay, a little bit. All right. So CRDTs basically come in two flavors, state-based and operations-based. And essentially what they are is data structures modeled after semi-lattices that have the semi-lattice properties of merging cleanly and being associative and commutative and idempotent and all of those things, and observe monotonic growth either in state or value depending on which CRDT you implement. So these are really, really awesome for distributed systems because we have to deal with the network dropping messages, we have to deal with the network reordering messages, we have to deal with the fact that we can't reason about when things will be observed because we don't have reliable broadcast in all cases. We definitely don't have atomic reliable broadcast, and we have some causal guarantees, but not necessarily fully, like something that fully characterizes causality. So an example of CRDT that later is kind of realized to be a CRDT but wasn't originally is vector clocks. So vector clocks basically are logical clocks that track order of operations in a distributed system. And they're basically IDs that monotonically increase. When you have divergent copies, you merge them together and then you take a pairwise maximum across the data structures. So they end up resolving to the correct value no matter how the updates are observed in the network. So what is this Derflow thing, and then how does it relate to this CRDT work? Why are we even doing any of this work to begin with? So the idea is that, in Erlang, if you generalize kind of the problem to Erlang, we have this message passing model, and the messages are going to arrive in various orders. And we want to ensure that the computation ends up being correct or coming out with some deterministic outcome. It's very hard to prove these things. QuickCheck is one utility that tries to exhaust the state space and then shrink to minimal failing test cases. Other approaches are the Conqueror work Solid that Costas is working on to try to prove that the ordering is correct in things. And we have our own work at Basho on a React test, And React test is like, you know, it's not nearly as exhaustive as any of those things, but we try to point out like the very specific distributed cases. So when we combine all these tools, we think we get something. But it's still, we can't prove that in all cases it's correct. Distributed Erlang also has some interesting semantics. Hans wrote a paper on it that I absolutely love that talks about all of the message ordering guarantees that you get and how some of those don't necessarily hold in the event of failures, and you know, it's all based on net tick time and all these fancy things. So it's really, really hard to prove these things. And the idea is that OTP brings a bunch of programming patterns to kind of reduce this uncertainty, allow us to write things in a way where we don't have to be as concerned about the problem. But it still does exist. So what are the contributions of the work? So this is the first part of this work to build this programming language that operates over these semi-lattices. So we propose it's an alternative approach to non-determinism. Kind of skirting the lines of truth, but whatever. You know, we say that basically, if we can fault-tolerantly distribute these things across the cluster on top of React core, we can show that we can make sure that the computation will end up being correct for some definition of correct. So I have to go fast. There's a lot of slides. I'm not going to get through all of them, but you know, so dataflow programming has existed for a while. We've had CTMCP, which is Peter Van Rooij's work in the MIT book, which produced Oz. Akka has some facilities for this. Ozma is the Oz model on top of Akka. And you know, you have the history there if you're interested in how that works. So the dataflow programming that we'll talk about is based on this single assignment story here. So you have a bunch of variables, and we're going to start with every variable being single assignment, which is, you know, you could think of this as a lattice with two states. Either it's bound or it is unbound. And we have this idea that things can be partially bound, which is that you're bound to something else, and then as you know, as we do the evaluation of the program and one changes, we basically propagate that out and change those in lockstep as best as we can. It being single assignment and that things are immutable and you can't bind them twice makes that really easy, and that's where things get interesting with lattices and monotonicity and all sorts of stuff like that. So you know, this is just kind of what the data structures look like. We store values, we store waiting processes, which are other Erlang processes that are blocking on a receive, waiting to be notified of a message. So if you go to issue a read, you're going to wait if that variable is unbound. If it's bound, you'll get the value immediately. Once it is bound, you'll receive a message. So we enforce the synchronizing in the language by using receives that will block forever. So it is not a deadlock-free model by design. And this bound variable is just used to bind things together. So this is the idea of the partial binding. You bind a dataflow variable to another dataflow variable. So the primitives, we have a declare, we have a bind, pretty easy. Here's how we go about updating everything. Should be fairly straightforward. Read will be a blocking operation to wait until a bind is called. It will use an infinite receive. Thread is basically just the spawn primitive in Erlang. We already have a facility to launch something in another process, and we can block on that process. We can extend the model with streams. This is straight out of some of the CTMCP work, if you've ever worked through that. You know, we have a stream of dataflow variables. Each variable references the next variable, so as you consume the stream, you basically block that, and you block on those values being available. So you'll block on until you get the end of the stream, and you'll block on each of those values waiting to be bound. Produce, consume, just the two primitives that you use. It's basically just a declaration of the dataflow variable, and then a bind of the variable, and a read of the variable. We also can do non-strict evaluation. There's an example of where a non-strict evaluation might be interesting in the paper, but we won't really talk about that because you can kind of just think through that as very smart engineers and researchers. So failure handling is interesting because it kind of adds non-determinism to the model. If processes are dying all the time and things like that, it gets very, very difficult to ensure things, especially across the network. So here's an example that we can ensure progress. You know, something is supposed to bind a dataflow variable, it dies, a bunch of things are waiting on it, obviously the model deadlocks, so what do you do? So we kind of classify these errors differently. We have these computing process failures where, you know, we're going to read a variable, we're going to perform a computation and then bind something else. You know, if we never bind because of a processing failure, we can re-execute that. But if it's fundamentally because the code is not working because it's a bug, you'll be stuck doing that forever. So we can't even restart the tree. So what we do is we use supervisor trees to basically restart the entire thing. And since that single assignment store is persisted somewhere that's outside of the flow of all these processes, we can restart a ton of them, and if you reissue a bind for the same value, it won't change. If you reissue a bind for a different value, you can either throw an error or ignore it and use the value. Depends on how you want to achieve the determinism. Another one is, we have this production of a bad value that causes the system to kind of get into a place where it can't proceed. So we've looked at extending the model with a non-usable value that you can extend, but that that's up to the programmer. So the API, all of these really non-idiomatic things that we have here, because we have a lot of people working on the project who are not Erlangers, have been fixed in the release that you can currently get on GitHub. So you just see you have a declare and it returns will be like OK term, and then you can bind to a function. So this will execute the function, bind it to the value. You can read, produce values, consume values. The laziness operator, it's just wait needed, and you'll just say, and then it will basically lazily realize any of the functions, so the things will be stored as functions. And then when you call the thing to read, it will go and realize all those values. So how do we make it distributed? So the partitioning strategy. So we have 3 options. We can have variables live at home processes and only have them once across the network and then send messages to them. We can have things that route messages to them. We can store all the information about them and globally replicate that state, but we don't do any of that. So what we do is, similar to the React data store, we partition the variables. So when you declare a new variable, we generate a unique identifier for it and place it somewhere in the distributed cluster. And then we know where to go because we use a consistent hashing mechanism. So we looked at 2 possible ways to implement this. So there's React Core, obviously. I'm sure you've all heard a lot about that if you've been to Erlang Workshop or Erlang Factory before. The other option was Amnesia. Amnesia has a bunch of problems under network partitions. That's been thoroughly documented either by Thomas or Hans. One of them did, and Ulf as well. It allows independent progress of the Amnesia nodes as the thing's running. So if you have a partition on the network and you have concurrent writes to either side, that's really bad, because we don't know how to reconcile them. We don't have a mechanism like vector clocks or something like that to reason about it. This is not a problem in a single assignment store where things are immutable if all of the functions are pure. If they're not pure, it's a problem. And when we start moving to CRDTs, where we can have things progress a certain way, not all CRDTs necessarily can be merged without causality information. So some of the simpler ones can, but some of the later ones require a bit more complex causality tracking mechanisms, which we won't be able to get into today. But and Amnesia kind of scales not super well, or the way that we want it, so to have things partitioned and kind of get linear scalability of the store itself. So we went with React Core. It's got consistent hashing. It's the implementation of the Dynamo paper. It's got causality tracking mechanisms. It's got mechanisms for handing data off between nodes when things move around the network, when you have failures, dynamic membership, all of this stuff. So again, obligatory ring picture for everybody who hasn't seen one of these before. React Core is a distributed hash table. We basically run a claim algorithm so that we give a bunch of these partitions to particular nodes in the network. What we do is, if we write a value to this, we will replicate the value to partitions that are adjacent on the network. So if a value gets written into this green partition, we'll also replicate it into this blue and yellow one, given a replication factor of 3. And all of that stuff's configurable. It uses consistent hashing to determine how to hash values. So any node in the cluster can know where a value should be stored. So it's not using some modulo thing or anything like that. And that reduces the amount of data we have to move. And what we have is the ability to kind of, these partitions can move between nodes, and the framework that's written in Erlang provides a mechanism to move that data around, know where things has to go, and help coordinate all that data being moved. So how do we implement the single assignment store across the cluster? So we perform writes of dataflow variables against a strict form of the replica set. So we do not use fallbacks. So fallbacks are a mechanism for another node to take a write for a particular node that might be down. We don't use that. We write to primaries only. So every variable has a replica set that is responsible for storing the data of that node, and we ensure that we can write to a strict form. As variables become bound, so as we start binding those values to these immutable, once we start binding values to these dataflow variables and they become bound and therefore immutable, we notify all processes and we perform the notification also using a strict form. If they get notified multiple times, that's fine. If one of the nodes performs a notification, we can exploit redundant, redundantly sending those messages, right? Because we know that it will be deterministic. In the event of node failures, we use an anti-entropy mechanism that will basically say, well, this node's coming back online. He was waiting to hear from these people, and he needs to notify these other members in the cluster that he has some values that might have been bound. So we basically walk the single assignment store and perform the notifications as we do the handoff or the repair. We do not make progress under network partitions. So you need to be on a majority partition for the system to make progress. If you are on the minority partition, we will not make progress as a safety guarantee. So we're sacrificing liveness and providing safety. In the event of a failure, again, we can restart a bunch of the computations and not have to worry about the redundant computation. And this dynamic membership, the duplication notifications are fine, so we can send the data to another node and say, hey, do some of this work for me, and kind of transfer that data around the ring. Okay, so here's just an example of what, if you want to see what the API kind of looks like. So there's like a concurrent map that's going to spawn a process here to apply some values. So it's going to, you have a stream that has input values, you have a stream that has output values. We're going to consume a value off the input stream. We're going to write a value into the output stream, and we're going to perform the computation. All those computations will be in separate processes. So we preserve the ordering of the values in the input stream to the output stream by doing the concurrent map. So it's kind of like a promise, right? Okay, so the future work. So so I wrote this. We wrote this paper in May. I've been working on it since then, and a lot of things have changed. So if you happen to go look at the code, and it's available on GitHub and it's free, a lot of the things we talked about won't necessarily be there anymore because we believe we found some better ways to do it, and the use case has slightly changed. So this idea of generalizing variables as joint semilattices. So we said that we want the bounded joint semilattices for the CRDTs, the state-based CRDTs, but this idea of the mutable variables are essentially semilattice with two states, the bounded versus the unbounded state. In generalizing this, now the computational model is slightly different because we want it to be deterministic, knowing that we get the correct outcome, regardless of scheduler interleavings, regardless of doing recomputations of part of the nodes in the cluster. So variables get bound to a particular value, and they can get bound to a secondary value if that value is a strict inflation of the lattice. So if you have a natural number lattice where you go from 1 to 2 to 3 to 4, if you bind to 1, and then we execute a bunch of computations based on that, you can rebind that value to 2. If you bind it to 1, nothing happens. If you bind it to 0, the bind fails. In addition to that, similar, so with the LVARs work, LVARs provides a mechanism to do a threshold read. So you say, I want to do a blocking read based on knowing that this value will be at a particular thing. So if you have a lattice that's going from 1 to 2 to 3 to 4, you basically block on that saying it's 3, and then you read 3 at that time. And then if you read it again, that process happens to try to read it again, that value is frozen, and then it will not proceed. So what we do is, rather than partitioning the data store, now we push a copy of the program to every single node in the cluster, every partition in that ring. Every partition in the ring gets a copy of that data. And it allows us to perform the computation, so distribute the values of the computation, and then join those values at the end using the merge properties of the semilattices. So that is the current state of the work. That's what we're working on right now. This is the new distribution model. We also have an alternative syntax that we're investigating as well. I hopefully already did make the library idiomatic. I encourage you to check it out, or check out any of the references. And I'm basically out of time, so thank you.
We have time for some questions.
Yes.
When Lindsay Cooper did this LVARs work in Haskell, she was very interested with her colleague Ryan Newton in doing this on a distributed setting, which is exactly what you've done.
Yes.
So have you told Lindsay what you've been doing?
Yes, I'm friends with Lindsay. I told her about this paper last week in San Francisco. So She's aware. She's not aware of the newer work I talked about at the end of the talk, because that's subject of a presentation that will be happening in October. But yeah, she's very much in the know about the work and was very excited about it, and we cited her. Yeah.
So in developing this, any fun like example applications you implemented, like
So the language for the paper, there are a bunch of example applications that show how you can do some concurrent operations and preserve some determinism and correctness. I don't remember what all of them are offhand. What we're working on now is trying to say, so if you think, if you're familiar with React and you can imagine something like the computation done to generate an index for 2i, we imagine that this work is directly related to that. So that is kind of the direction we're moving, but none of the example applications are like super exciting in my opinion. Yes?
Can you say something about the throughput and
The performance? I have not benchmarked the performance at this point because we're still adjusting the distribution model. So that's an excellent question, and yeah, it was omitted because specifically of the distribution model stuff. Is that we tried this is the third distribution model that I've implemented. So the paper was the first one. There was a second one that I implemented last week, and the one I talked about today I implemented on the plane here. So yeah, man, you guys are getting the cutting edge. Perfect. Okay, well, thank you very much. Appreciate it.